Although the HSB colour system is very natural, most computer systems use the RGB system. The RGB system uses three primary colours: red, green and blue. And the RGB system is additive. That means that when all the primary colours are mixed, you get white. Imagine shining a red light. If we add a green light, we have red and green. But where the red and green overlap, we get yellow. When we mix red light and blue light, we get this purple colour. This is more commonly known as magenta. Here we see the red, green and blue together. Notice that where green and blue mix, we get a light blue called cyan. More importantly, however, where we have red, green and blue all together, we get white. With the RGB colour system, we can describe a colour numerically then by specifying how much red, how much green and how much blue is in the colour. Most RGB systems use 8 bits for each colour, so we have values ranging from 0 to 255. With this colour here, the red value is 255, the green is 0 and the blue is 0. So it's pure red. Here, the red value is 150 and the green is 0 and the blue is 0. So there's only red in this colour, but not as much as in the previous colour, which was 255. So this is a darker red. Similarly here, there's only red in this colour, but with a red value of 80, this is a long way off pure red, and so you can see it's much darker. Here we have a red value of 0, a green value of 255 and a blue value of 0. So this is pure green. Here we have a red of 0, green 178 and blue is 0. So there's only green in this colour. But it's not the maximum possible green. Here we have red 0, green 96 and blue 0. So this is a dark green. This colour has a red value of 0, a green value of 0 and a blue value of 200. Now 200 is nearly the maximum of 255. So this is very, very blue. This colour also only has blue in it. It's red 0, green 0 and blue 50. But that blue 50 is actually a very low value, and so this colour is almost black. Here we have a red 255, green of 0 and a blue 255. When we mix red and blue together, we get magenta. Here again we only have red and blue. Here we have a red of 150, a green of 0 and a blue of 150. So like the last colour, this doesn't have any green in it. And so it's like the magenta colour we just saw, but because the values are lower, it's much darker. Here we have a red of 255, a green of 255 and a 0 for blue. That gives us pure yellow. When the red and the green and the blue are all at their maximum possible values, we get white. And when there's no red, no green, no blue, nothing at all, we just have black. Now, if the red and the green and the blue appear in equal proportions, we get a shade of grey. We saw that when the red and the green and the blue were all 0, they were black, and when they were all maximum, it was white. So if they stay in equal proportion, then we get something that's between black and white, a shade of grey. So here we have an RGB of 200, 200, 200, and this is a light grey. Here again, the red and the green and the blue are in equal proportions at 150 each, but this is darker than the previous grey. And with red values of 80, green values of 80 and blue values of 80, this grey is quite dark. Consider these values here. If the 255, 150, 150 was in fact 150 for red, 150 for green, 150 for blue, then what we would have is a shade of grey. If you imagine this value as being 150, 150, 150, but with the red turned up a notch, well then it makes sense that this would be a kind of shade of grey, but with extra red in it. And of course that would give us pink. At 255, 150, 0, this colour has no blue in it at all. Okay? It has maximum red value and a fairly high green value. Now, if the red and the green appeared in equal proportions, then it might be some shade of yellow. So it makes sense that if you had a yellow with the red cranked up a notch, you'd get orange. So from looking at the RGB values and knowing what we know about the primary colours and what happens when they mix together, it's possible to hazard a guess sometimes at what a colour will look like based on the RGB values. So here's a few exercises for you. Here's an RGB value and 4 colours. See if you can figure out which of these 4 colours these RGB values belong to. Can you tell which of these 4 colours belongs to these RGB values? How about these? How about these? Try these ones. How about this? How about this? How about these? Try these ones. The LAB colour system also uses 3 variables. In this system, however, 1 variable is used for the brightness or lightness, and then 2 variables are used to deal with the colour. The L value in the LAB system tells us how light or dark the colour is, using the kind of measures we would have used when coding grayscale images. L typically ranges from 0 to 100, with 0 being black and 100 being a bright colour. The other 2 variables then, A and B, control the actual colour. The A value represents a scale from green to red, with green having a value of -128 and red being +127. Now, these numbers seem a bit strange until you realise that that range gives you a total of 256 possible values. Now, the B value represents a scale ranging from blue to yellow. The blue end is minus 128 and the yellow 127. The LAB system is closer to the kind of colour that's used in analogue television. So some people prefer to use the LAB colour system when they're designing graphics for DVDs, for example. The main advantage of LAB colour, though, is that a black and white version of an LAB image can be very easily generated just by extracting the L values of the pixels. To get black and white versions of an RGB image, for example, you might have to get the average of the red, green and blue values. Now, the HSB, RGB and LAB colour systems are additive. When we add colours, we're adding more light to the darkness that would have been there if we'd nothing. Okay? So with additive systems, higher values usually mean brighter colours. However, when you first saw the RGB system, you might have been surprised by the choice of primary colours. When you were at school playing with mixing paints, you learned that the primary colours were red, blue and yellow. If you mixed yellow and blue together, you got green. Well, it turns out that mixing paints is subtractive. If you mix two colours of paint, the resulting mix is darker than one of the colours. In an additive system, the more you add, the brighter it gets. In a subtractive system, the more you add, the darker it gets. So that's how it is for paints and for printing ink. CMYK is the colour system used in the printing industry. It uses 4 colours of ink printed on white paper. C is for cyan, a kind of blue. M is magenta and Y is yellow. It's no coincidence that the primary colours in the CMYK system are the secondary colours of the RGB system. The fourth value K is for black ink. In theory, you could probably produce black ink using just cyan, magenta and yellow ink. But it's much easier to just use black ink. The C, M, Y and K values are usually expressed as a percentage from 0 to 100. If all of the values are 0, then there's no ink on the white page, so the colour is white. 100% cyan and no other ink would give you cyan. 100% magenta and no other ink would give you magenta. And of course 100% black would be black. When it comes to mixing the colours, think back to your childhood when blue and yellow made green. Bright colours then can be darkened by simply adding black. Here are some more exercises. Which one of these colours is the one represented by the CMYK values shown? Here's another one. Which colour goes with these numbers? Here's another one. Which of these colours goes with these values? Try this one. How about this? When coding images, the different values used to represent the colour are stored in separate channels. This means that an image stored in RGB format would have the red, green and blue stored as if they were three separate images. So it would be like having three grayscale images that are all slightly different. Only when they are all combined then do the colours fall into place. Image editing applications like Photoshop let you examine and edit each of the colour channels of an image independently. Now, this can be really useful if you want to alter the colour in subtle ways. Here we can see the red, green and blue channels for this colour image. Here's another colour image, and here are the red, green and blue channels. Notice that pixels that have a lot of red in them show up as being bright in the red channel, and pixels that have almost no red in them show up as being dark in the red channel. Similarly for the green channel, if the colour is green, then it'll appear bright in the green channel, and if there's no green in it, it'll appear dark in the green channel. Here's another image coded using the RGB colour system. Now, can you tell if the channel shown here is the red one, the green one, or the blue one? What about this one? Is this the red channel, the green channel, or the blue channel? Here's another one. How about this? Here's another one.